Hello guys, welcome to Ramta Solutions. Welcome to your grade 10 electric circuits. In this video, we are going to introduce some of in fact it's a revision. The first thing that we're going to do in our introduction, it's a revision of what you did in the lower grades and how you see circuits, and then proceed to defining potential difference, what it's about and all that. Then proceed to defining current, what it is about. You will get to see more of it. You will then get to see also what is resistance. And to conclude this video, we are going to look at some fewer examples, maybe 2 or 3 examples. Okay. And of course, we will try to summarize everything that we have learned in this. So without any waste of time, let's get into it. So for our introduction, I want to remind you that when you were in the lower grades, you used to see, so these were the drawings that you made, and this represented what? This represented a battery. Okay, so when you see this, you see a battery. Right, it represented a battery. And when you see something like this, a V, it represented a voltmeter. Okay, it represented a voltmeter. This represents a current measuring device, which we call an ammeter. No, in fact, I should say which we called, because it's what you learned about in the lower grades, which you called an ammeter, right? You also learned about this here, or sometimes we had it in this way, where we had letter R in a circle. This represented a resistor, right? And we also had this one here, which represented a. Then we also had this one here, or what was this? This was a switch, right? This was a switch, with this one here being a closed switch and this one being an opened switch, right? So these are the things that you used to see in the lower grades. Okay, and of course, as we proceed in this video, you're also going to see some of the things. And I also recall that in the lower grades, you were able to use this formula R equals V over I, where you said this guy is a resistance, you remember? And you said resistance is measured in omega, which we called ohm. This was potential difference. Remember, guys, it was potential difference, which you measure in volts, capital. This was current, right? This was current, which you measure in capital I, right? Yeah, which you measure in its unit is capital A for ampere, right? Capital A for ampere. So these are the things that you learned in the lower grades, right? These are the things that you learned in the lower grades. Now we are going to give more meaning to these things. Okay, so without any waste of time, let's proceed. We're going to item 2, which is potential difference. Okay, going to item 2, which is potential difference. So this is potential difference. Now, potential difference, when we talk potential difference, first thing first, I need to give it a definition. So potential difference is energy transferred per coulomb of charge. Or maybe, let's call it that, energy transferred. It is energy transferred per coulomb of charge, right? Per coulomb of charge. Or you can use this one, you can say it's basically, what is this, work done per charge. Okay, you can say it's work done per charge. You can say it is work done per charge. Or simply, you can say it is work done in moving a unit charge between 2 points. Work done in moving a unit charge between 2 points. Okay, between 2 points. Right? So all these are definitions of charge, but potential difference, potential difference. They are all definitions of potential difference, but I'm still going to add more information to this. Now, another thing that you should also know, it is sometimes referred to, what is that? Sometimes potential difference is referred to as voltage. Okay. Sometimes it is referred to as voltage. Sometimes it is referred to as voltage. Okay, sometimes it is referred to as voltage. Okay? All right. So I'm saying sometimes it is referred to, oh boy, sorry about that. Sometimes it is referred to as voltage. And then what should we say? We should say now the symbol to represent potential difference is capital V. And what is the SI unit? So the SI unit is small letter volt, but capital letter V, that is the unit. Okay, the unit is capital V, which represents volt. Okay, so that is the SI unit of potential difference. Okay, now it is measured using a voltmeter. It is measured using a voltmeter. Okay, it is measured using a voltmeter. Now let me go back to the apparatus you used to see in the lower grades. We represent a voltmeter with this side. Okay, so this measures potential difference. Okay, now this definition is giving us the formula of potential difference. So we said potential difference is work done per unit charge. That means, check this out, potential difference, okay, potential difference is work done. When they say per, it means divided by charge. Therefore, this means V is equal to, oh boy, this means V is equal to W over Q, Q for charge. So this is your formula for potential difference. Remember, this is work done. It's measured in, this is work done. It's measured in joules. Joules have the symbol J, and this is charge. Charge is measured in coulombs. Okay, in coulombs with the letter C. Okay, and of course I told you voltage is measured in, or potential difference is measured in V. Okay, all right. So now this is all that you need to know regarding potential difference. But let's also now talk about M. Let's talk about M. Okay, let's talk about M, which we say it's electromotive force. Okay, let's say it's electromotive force, but wait a minute. It is just not that. Why do we use M in electric circuits? In electric circuits, we will say this. So the definition is it is work done per unit charge by the source. Okay, work done per unit charge by the source. By the source. What is the source? In this case, the source is the battery. Okay, now something that you need to know, it is constant. Okay, oh boy, it is constant. What do we mean by that? We mean it doesn't change. The potential difference applied by the battery remains the same. Okay, the potential difference applied by the battery remains the same. Okay, this is what we mean. Okay, this is what we mean. Right. All right, perfect. Now, I'm also going to add, maybe I should add this. I'm also going to add question here. Why do batteries go flat? Since we're talking potential difference, why do batteries go flat? Right? Why do batteries go flat? That is the question that we should ask. Okay? So that is the question that we should ask. And I'm going to give you guys an opportunity to really tell me, why do batteries go flat? And the answer is simple. Something that you know, guys, is this. Batteries store chemical potential energy. And when they are in use, that chemical potential energy is converted to electrical energy. Right? Therefore, when the battery goes flat, what it means is that all chemical potential energy has been converted to, I'm going to say, to other forms of energy, because it doesn't necessarily mean that all energy is converted to electrical energy. So I repeat, the main reason is that when a battery goes flat, all potential energy has been converted to other forms of energy. So I'm going to say this. Note, first, I'm going to say note, batteries store chemical potential energy. Store chemical potential energy. Okay, batteries store chemical potential energy. All right. Now, when in use, batteries convert chemical potential energy to electrical energy. All right, to electrical energy. All right, to electrical energy. All right. Now, when they go flat, it is because all chemical potential energy has been converted to other forms of energy. All chemical potential energy has been converted to other forms of energy. Okay, that is it. There you go. That is the reason why batteries go flat. Okay, that is the reason why batteries go flat. Okay, perfect. So now let's proceed. We go into current now. We go into current. So item 3, current. Now when we talk current, so we'll talk current now. What is current? And the definition of current is It is the amount of charge passing through a point or passing a point in 1 second. Okay. It is the amount of charge passing a point in, not just a point, passing a fixed point. I should fix that as well. Passing a fixed point in 1 second. Okay, passing a fixed point in 1 second. Another one could say it is the rate at which charge moves past a point a second. So, or rate at which charge moves past a point, not just a point, again, a fixed point. Moves past a fixed point, right? Move past a fixed point in a second. Okay. These two definitions, guys, they really mean the same thing. Okay. Now, proceeding, there's something that I also want you to highlight when it comes to current. Its symbol is capital letter I. Its SI unit is ampere, capital letter A. It's measured using an ammeter. Okay, it's measured using an ammeter. Let me go to the first page so we can see what an ammeter looks like as a reminder. So this is an ammeter. Okay, this is an ammeter. Okay, all right. So current is measured using an ammeter. Okay, so we can therefore have a definition. We can therefore have a definition or a formula. We said current, right? We said current is the rate. What did we say? We said it is the rate at which charge moves past a fixed point. When we say rate, it means we will have delta T. The rate at which charge. Oh boy. So this will be charge. Oh my. Charge over time. So what is this? Current is I, charge is Q, and then what is time? It is delta T. Alright? We have said that you know that the units of current are amperes, the unit of charge is coulomb, and the unit of time is second. Right? So this is time in seconds. Okay, this is time in second. Yes, and of course this is charge in coulomb C. By now you know. And of course this is current in ampere. So this is the formula that we're getting from the definition. Okay, this is the formula that we are getting from the definition. Okay, so I want you to know that current flows from the positive terminal. Current flows from the positive terminal, okay, of battery. Okay, it flows from the positive terminal of the battery. Something that I want you to know of the battery. Okay. Then it depends on what is connected in the circuit. It depends on what is connected in the circuit. It depends on what is connected in the circuit. So current will change depending on what is connected in the circuit. Okay, depending on what is connected in the circuit. Now, I will also tell you this. So by saying this, I basically want to say to you, a battery does not provide the same current. Okay, a battery does not supply same current. Like I said, current depends on what is connected in the circuit. Okay, it depends on what is connected in the circuit. Okay. While we are on it, I should also add this. Current does not flow in the voltmeter. Current does not flow in the voltmeter. Current does not flow in the voltmeter. That's one thing that you should know about it. Okay. Happy? Right. And I think when we are on it, I should also mention that it gets divided based on, I'm going to say, joints. This you will get to understand in the next video. Gets divided, I'm going to say, across joints. Okay? Across joints. You're going to see this later. I'm going to put joints because it's a word that I'm using loosely. Yes, it's an English word, but I'm using it loosely. Current gets divided across joints. You are going to see that later. I believe in the second video, the video after this one, you will get to see that. Okay, that current gets divided when across joints. Okay, you will get to see that. All right. So, this is all we can say concerning current. Okay. This is all we can say concerning current. Okay, this is all we can say concerning current. All right. Now, I'm going to look at resistance. Let's go together. I believe it's the fourth item. Is it the fourth? Yes, it's the fourth. The fourth item is resistance. So the fourth item is resistance. Let's look at it. Resistance. Ooh, what is it resisting? Resistance. So what resistance does? I think it's too small, ne? Yeah. Resistance, what does it do? So basically resistance is, it's basically slowing down the flow of charge in a circuit, okay? It slows down the flow. Okay, it slows down. It slows down the flow of charge in a circuit. Okay. Okay. So basically, when we talk of resistance, we are basically saying we are talking the measure of how much the flow of charges is opposed in a circuit, or we basically say how hard it is to push electricity through a circuit element. Okay, so we'll say it's a measure of how hard to push electricity through a circuit element. Right, through a circuit element. Okay. Or you can say it is the measure of how much the flow of charges opposed in a circuit, right? A measure of how much the flow of current opposed in a circuit, whether in a circuit or circuit element, it doesn't matter. Okay. Right. So this is what we are looking at. We are really not going to look at factors affecting resistance, okay? We are not going to really look at that, but maybe let's look at them quickly. Let's look at them quickly. Factors affecting resistance. What are they? Factors affecting resistance. What are they? One, the cross-sectional area. The cross-sectional area, I'm going to leave a slight space. The cross-sectional area and length. Okay. The cross-sectional area and length. Okay. So, cross-sectional area, is basically indirectly proportional to resistance. The greater the cross-sectional area, the lower the resistance. The lower the cross-sectional area, the higher the resistance. Now, with regard to length, basically length is directly proportional, or resistance is directly proportional to length. Okay. Resistance is directly proportional to length. So if length of the wire increases, resistance increases. Okay. Now, in general, we can say R is directly proportional to A and indirectly proportional to the cross-sectional area. Okay. This is what we can say. These are the factors affecting resistance. Okay. Now, when we talk resistance, did I mention? Oh, I didn't. Now, as I proceed, let me do this. The symbol of resistance, symbol is letter capital R, and then the SI unit, I should write it like this. SI unit is ohm, which is the Greek letter omega, okay, which we call ohm, okay. And then it's measured using a resistor. So in your circuit, it is represented in this way. Let me show you. In your circuit, it's represented in this way or simply in this way. Okay? That is your resistor. Okay? Did I say resistance? I think I heard myself saying resistance. It's measured using a resistor. Perfect. It's measured using a resistor. Okay, so the formula that we have been using all along is this. A resistance is equal to V over I, meaning 1 ohm is equal to 1 volt per ampere. Okay, so you know all these things now. You know all. Okay, you know all these things. Okay, so something that I want to tell you before we proceed further, you know that we said V is equal to W over Q. This therefore implies we can say W is equal to VQ. Not? Again, we said I is equal to what? Is equal to Q over delta T. This therefore implies we can say, or let me move this guy. No, I don't have to rewrite. Because I think I do have a tool that moves. Yeah, I think I do have a tool that moves. Yeah. Yes. Is it the one? If it's not, okay, it's fine. Let me erase them there. Keep forgetting how these things operate. So we said I is equal to Q over delta T. And I'm also noting we said R is equal to V over I. So here we can say Q is equal to I delta T. Now I want you to follow me here. Now here we can say, oh, we see this V, that when we want the work done or the energy transferred, we can say it's V times Q. But we did say that Q is equal to IT. So this W can basically be this W can basically be, where there's V, where there's Q, I'm going to put I delta T. So it'll be V I delta T. So you see, now I'm expanding. Now, okay, I don't have a V given. I have, let's say, yeah, from this formula, we find that we can say V is equal to R I or IR. So that means from here we can say, oh, if I don't have V, I can basically call this, let's see, what can I call it? I can call it RIQ. Right? If you have Q, so let me say this, you can call it W equals RIQ. Or simply, moving on from this one here, it can be W equals V, not V, we said now in place of V we put RI. So this is RI, I delta T, which will be RI squared delta T. Okay, RI squared delta T. Right? So it can be like this. Okay, now it happens that you don't have current and you also don't have Q, but you have time. And if you don't have current, this formula can be in the form I is equal to V over R, isn't it? I is equal to V over R. So how would you do this? It will basically be, let's see, from this one here, we can say it's V into, where there's I, we say it's V over R times delta T. What is this? This will basically give us V squared over R delta T. So remember, guys, what I'm doing here, it's basically manipulation. Okay, it's basically manipulation, mathematical manipulation of formulas, and they make sense. You can use that. So, in summary, the formulas we are using, the formulas that we are using would be V equals W over Q, and it can also be W equals V I delta T. We use I equals Q over T. We also use R equals V over I. Then we can play around with them to find whichever that we need if we are lacking whichever. Okay. So these are the formulas that you use. Now, without any waste of time, let's try examples. I believe it's item 5. Let me confirm. Okay. It's item 5. Examples. Examples, it's item 5. So example 1, or let me call it example A. Calculate the resistance if the voltage is 12 volts and the current flowing is 6 amperes. So our answer here, as you can see, we are saying R is equal to V over I. So what is our answer? The voltage is 12, or potential difference is 12. What is current flowing? The current flowing is 6 amperes. 12 over 6 is 2. Therefore, the resistance here is 2 ohms. Okay, the resistance here is 2 ohms. Okay, The resistance is 2 ohms. Okay, the resistance is 2 ohms. Right? Moving on. Example B, I will say a 45 coulomb charge moves past a point in 1 second. In 1 second, what is the current in the second? What is the current in the second? So, our solution, looking for, and we're given charge and we're given time. So this is current I equals Q over delta T. So what is Q, which is charge? It's 45 coulombs. And what is time? The time is 1 second. Therefore, the current flowing is 45 amperes. Okay. The current flowing is 45 amperes. Okay. Now, number C. Let's try number C. Number C, a battery transfers. A battery transfers 120 joules of energy. 120 joules of energy to a 10 coulomb charge. To a 10 coulomb charge. Roman figure 1, calculate the voltmeter reading. Calculate the voltmeter reading. Roman figure 2, calculate the ammeter reading. Calculate the ammeter reading when the 10 coulomb charge, passes the ammeter in 5.18 seconds. Now, our solutions. Roman figure 1, the voltmeter reading, meaning we're looking for V. We know V is equal to WQ. Okay. Now, what is W? The energy transferred is 120 joules. And what is the charge? The charge is 10 coulombs. Okay. So this will be 120 joules over 10 coulombs. What is this? This to me looks like 12 volts. To me, this looks like 12 volts, isn't it? This looks like 12 volts. 120 divided by 10. Yes, it's 12. Now, calculate the ammeter reading when the 10 coulomb charge passes the ammeter in 5.1. Roman figure 2 will say current is equal to charge over delta T. What is the charge? It's 10 coulombs. Now, what is the time? It's 5.18. Let's see. What is our answer? Our answer is simply, it's not simple. I have to use a calculator here. 10 divided by 5.18. What is it? It is 1.93. It is 1.93 amperes. It is 1.93 amperes. It is 1.93 amperes. All right. So this is it, guys. I hope you will enjoy your electric circuits. This is the introduction that you need. But stay tuned for the next video, which will be looking at resistors connected in series. So with that being said, it's a wrap and bye-bye.